How do engineers determine system model fidelity? Imagine trying to recreate a complex machine with just a simple sketch. How do engineers know if their digital version truly matches the real thing? That's what we're here to find out. When engineers build models of systems, whether they are mechanical, electrical, or control systems, they need to check how close these models are to reality. This process is called determining system model fidelity. It's all about measuring how well the model mimics the real system's behavior. First, engineers start by clearly defining what the model is supposed to representing. They call this the referent or the actual system. It could be a physical machine, a process, or even a hypothetical scenario. Knowing the purpose of the model helps decide how detailed it needs to be. For example, if the model is for designing a control system, it needs to be very accurate. But if it's just for initial concept ideas, a rougher model might do. Next, engineers verify and validate the model. Verification checks if the model was built correctly according to the design. Validation tests if the model's outputs match the real system data. They compare how the model responds to different inputs with how the real system responds. If the responses are similar, the model is considered valid for that purpose. To measure this similarity, engineers use specific metrics. Accuracy shows how close the model's outputs are to real data. Repeatability checks if the model produces consistent results over multiple trials. Resolution measures how much detail the model can representing. These numbers help decide if the model is low, medium, or high fidelity. The level of detail in the model also affects fidelity. Low-fidelity models are simple and use basic equations or empirical correlations. They give rough answers quickly. Medium-fidelity models include more physics, like conservation of mass and energy, and balance accuracy with computational speed. High-fidelity models use detailed physics laws and track individual components, giving very realistic responses but taking more time and resources. Uncertainty plays a role too. Engineers look at uncertainties in inputs and parameters. Some uncertainties are random, called aleatory, while others come from lack of knowledge, called epistemic. Understanding these helps gauge how confident they can be in the model's predictions. Refining the model is an ongoing process. Based on validation results, engineers update parameters, add details, or simplify parts to meet the fidelity needed for the task. This iterative process ensures the model is as reliable as possible for its specific use. Finally, engineers decide if the model is ready to be used for design, control, or prediction. They assess its trustworthiness and limitations. High-fidelity models help predict system responses more accurately, which leads to better control strategies and safer, more efficient designs. But they also cost more in time and computing power, so choosing the right level of fidelity depends on the project's goals and resources. In the world of mechanical engineering, especially when working with system dynamics and control, knowing how to measure and improve model fidelity is key. It ensures that simulations truly reflected what will happen in real life, helping engineers make smarter decisions and create better systems.